are actually uh, what I like to call as the alphabet, alphabet of the entire. I would like to call entire science, but since we are here, we would call it the alphabets of entire data science. So from today onwards, we will be moving on to building models. As I mentioned in the first and the second session, maybe a model is an idea. Okay, so we are going to focus on a specific idea for the next, starting from today, for a few sessions, we are going to focus on a very specific idea. What is this? To begin with, we are entering the domain of what is called supervised learning. That means we are going to, within quotes, train a model, and during the training phase, the expected outcome is also known, right? That's what supervised model is. So, and we are entering this field of supervised learning. And in this, for the first 2 or 3 sessions, we will be discussing exclusively what is called prediction task. That is, we want to predict the value for a variable that contains continuous values. Okay, say for example, I want to predict the salary, I want to predict the rainfall, I want to predict revenues, GDP, all these things. So these are continuous values, continuous numbers. So that we will restrict the usage of the word prediction for these kinds of values. Now we can also predict classes, categories. We will call them as classification tasks. So for the next 2-3 sessions, we will focus exclusively on prediction tasks. That means building a model that can predict values for a continuous variable. This is a very, very important task because a lot of our work is on this. Whatever kind of task we might do, we might be interacting with LLMs. We could be doing all these sophisticated tasks, but at the foundations of it, most often we are actually predicting some values. Okay, for example, all these LLMs that we have, all these either transformer-based models or these GPTs, like ChatGPT or Gemini or whatever. All these things, what they are doing is they are glorified next word prediction models. They use very sophisticated ideas, but essentially that's what they end up doing. And what is the foundation of that? They are actually predicting the probabilities at the very core level. Okay, at the deep levels, that's what they're doing. They're predicting probabilities for various next tokens or next words for simplicity. And then whichever whichever word has the highest probability, that's what is presented. Okay, so probability is a continuous number, right? It can vary from 0 to 1 in a continuous manner. So most of the tasks we do in all our exercises, is predicting a number. And that's what we are going to talk about for the next 2-3 sessions. Even though it's such a very, very important and foundational idea, I'm going to use a very simplistic example to drive concepts that form the backbone of what we are going to study. And the example I'm going to present is actually from this book. It's called Introduction to Linear Regression Analysis by Douglas Montgomery, Elizabeth Peck, and Jeffrey Vining. And I think it's called Vining. I do not know whether it's Vining or Winning. It's not Winning, I think. But however, his name is Jeffrey. That's easier to pronounce or unambiguous. So, so I'm going to present a very classic textbook example and introduce you to a variety of concepts that go into this idea, the very basic. Again, now you can think of these ideas as alphabets of supervised learning ideas. Okay, that's what we are going to look at for today and tomorrow. So the example might look like very simplistic, very contrived, and when you see the example, you can tell me whether it is contrived or not, and I can keep that as a question for you. But anyway, we'll meet that when you do this. If you had gone through the slides I had already shared with you, the reason why study AI/ML models, especially regression models, right? That's what we are going to study for the next 2-3 sessions. Why study regression models? There are lots of surveys in the past. This is done. I think this was taken in the year 2020, just before or 2021. The results. So data we have till 2020. Okay, so you can see of all the models at that time, GPTs had not become very common. The generative AI itself had not become very common, but let alone agentic systems, right? So it was just before the explosion of the generative AI ideas. When you see at the time, linear regression was the most sought after technique among all other different techniques that were being used during those times. For example, even CNNs, very sophisticated neural network ideas, which you will study in the next course, and GANs, which are like the elementary attempts at generative AI. All these, more than any of these things, very simple idea that we are going to study now was the one that was in high demand by data scientists, software engineers, machine learning engineers, business analysts, till about 2020. And if you see, even now, and I would surmise that this is going to be the case in spite of whatever wrapper we might use around all the prediction models. This is still going to be the case. That's what I hypothesize. So I want to just skip over these ideas, and you could go through this list of where linear regression to be used. Anywhere you want to predict a continuous variable, a number, you have regression. Okay, regression is the technique or is the method that we use whenever we want to predict this. For example, in very weird scenarios, like you want to predict the length of stay in the hospital for an inpatient based upon age, disease type, severity, etc. Okay, that's a linear regression problem. Okay, predicting the wafer quality in semiconductor manufacturing based on temperature, pressure, gas flow, all these things. Price for tickets, predicting dynamic flight fares. Okay, you can think of anything, any domain, anything. Regression is the technique that you would be using. But anyway, so what is regression? Regression is why don't we just use prediction, right? We'll understand the reason behind using the word regression in a short while. Essentially, whenever we want to predict a continuous value, then The technique is called regression. The technique we are going to use is called regression. Okay. So what is it? It is also sometimes called least square regression. We'll start with something called simple linear regression, or also called ordinary least square regression. What is this technique? This is a technique where we want to predict a value for a variable based upon values of another variable. That is, we want to predict the value for y based upon the value for x. We have only one x based upon one other variable, and that's called simple linear regression. So we'll start with this example, and you are going to get used to this idea that in all our courses, even next course and the other courses that we are going to deal with, you would see that we are going to so far initially I have introduced some definitions. For example, in probability and statistics. In statistics also I started with some examples. That's going to be our approach throughout. Okay, so in every course. So I'm going to start with this example. This is the example that I mentioned. I have taken from the textbook. Okay, that's an awesome textbook. If anyone is interested in going deep and understanding regression at a deep level, they should read that book. And more than reading the book, they should also solve the problems in that book. Well, anyway, I do not know whether you have the luxury of time for that, but here is an example. I think this is the first problem in the second chapter. First chapter is like an introduction. This is the first problem in the second chapter, and this is what it is. So a grocer collected this data of delivery times based upon the distance to the customer's place of delivery. So he had given distance in, I think, feet, and time in minutes. So I've just translated the distance, misappropriated his problem and used meters as a much more meaningful unit. Okay, I would like you to take a look at it and tell me the first question I'm going to ask you. Do you think it's a real data or contrived data? Give me your reasoning.
Can you repeat that question, sir?
Look at this data and tell me whether this looks like contrived data, or is it does it look like real data?
Contrived data.
And give me your reasoning why you think it's contrived or real.
No one would report time as 14.88 minutes. It's not a common method of representation for time.
So chocolate, virtual chocolate, like I said in the last class. Yes, that's correct.
Thank
so
you.
If you look at it, who measures time, especially in minutes, to two decimal places? Mohammed Niaz, please go ahead if you have a different.
Yeah, so if we say that the distance crossed by time, 36 is happening at 9.5 minutes, whereas 110 happens at 8. It seems to be, counter-logical.
Well, that's a good observation, but it is actually possible. Okay, think about this. Okay, we'll think about. We'll come to that in a little while. But that's what data usually looks like. Okay, some data is sometimes usually looks very haphazard. Looks sometimes random, but that's the data. Assuming these measurements were within quotes true, no, then it's possible. But the much more, the cleaner evidence I'm getting is like what Suvir mentioned. Who measures time to two decimal places in minutes? Now, you could say, I mean, somebody could go ahead and argue, no, maybe they measured in minutes and seconds and then converted into decimals in minutes. Okay, but still, I don't agree to this. Then we would have 60 by 100, right? That would be 60 seconds. You have to convert to minutes. So you would the decimals would be quantized to that. right? So we will be writing like, 100 units, you have to divide by 60 seconds. Therefore, that would be in, this will always go in 1.67, multiples of 1.67. Okay, so these are weird numbers. So this is a very clearly, it's a controlled example. Having said that, that's another very important observation that you see. On the one hand, you have distance, seeming to be increasing. So essentially what I have done is I have sorted this data in the increasing values of distance. But when you look at that, the time doesn't seem to be increasing consistently like the distance. Okay, it increases, decreases. Therefore, there seems to be some fluctuation in the time values. So that's another indicator. Maybe this is contrived. Possible, maybe, but I'm not too worried about that issue. Can you make some other one more? I'm looking for one more observation. If you can get me, this is going to be very, very important as we move along. Yes, John Sarani, please go ahead.
I think.
Sorry, I saw. Is it okay? Shall I proceed? Okay. The distance is actually in the sorting order. This is the one I saw this from the screen. So.
Yeah, that's what I have rearranged it that way. So
okay, you arrange it this way. And of course, in the earlier point, you're correct. Even though the distance is longer and might be the time is less, if you use a mode of vehicle, might be a flight or something like, then you can reach in faster time.
So that answers your question, Muhammad. Okay, so maybe we need another variable, namely mode of delivery. Okay, maybe for this 36 meters customer, maybe this fellow just walked, but for the one at 110 meters, maybe he took his motorbike. Okay, so we do not know. So maybe that's needed to really understand the delivery times.
Which indicates that it's incomplete data.
It could be an incomplete data.
Yeah.
It could be, but this is what we have as of now.
Sure, got it.
Okay, so that's another situation we probably will face in real data. Sometimes many a time what could happen is this: we start collecting data. Now data gets collected, but as things evolve, more and more variables get added. So data collected at earlier times might not have values for some of the variables. No, that's very common practice, right? So that's another issue so this example seems to allude to that kind of an issue. Okay. The one very important aspect I wanted you to focus on was this number 120, 150, 150. Seems like there are two customers who are at the same distance, but slightly different delivery times, right? Look at this similarly, 210, 250, 220. They are all within 10, 215 and 210, just 5 units difference. 215 and 220, only 5 units difference. But they all have very different delivery times. Same here, I saw something else here. 448, 450, practically the same numbers, but different delivery times. So this tells us another very important aspect, namely, so here is you should have gotten an implicit understanding now that the time of delivery depends upon distance, not the other way around, right? Yes, Siddharth, please go ahead, ask your question.
Nothing, I was just saying there are too many significant outliers at the face of it, right? So there is possibly an area that we need to call out. The mode of delivery is one. Then the area where the delivery is happening also is another data point that we need to have here, right? Possibly the weight or the weight of the package that is being delivered is another variable that we need to add here, just to have proper analysis.
Correct. And also the traffic conditions.
Correct.
Okay, so there are so many variables that are missing in this. Okay, but just for introducing concepts, we'll just look at this basic idea. Somebody else also had raised their hand. Who is that? If you have, please go ahead and ask your question.
Yeah, no, it's Leon. And just building on that same comment, there's so many variables, traffic patterns, even at the same distance, 150.
Yeah.
Assuming I'm delivering the groceries at the ground floor versus going up 4 levels, 4 flights to deliver to an apartment at a higher level.
Right.
So your point that you made, there's so many variables here that could be affecting the times that we don't know.
Right.
That was my point. Thank you.
So, but now what we will do is, just for understanding what all this prediction task is, we'll just restrict to this one variable, the distance, which is the independent variable, time, which is the dependent variable. So time of delivery depends upon the distance of delivery. Okay. So with that understanding, we see that for the same value for the independent variable, we could get different values for the dependent variable. For y, for the same value for x, we could get different values of y. Okay, so that's one observation I want you to keep at the back of your mind right now. Okay, let it be there. Now, given this data, if I ask you a question, okay, can you make a prediction for the delivery time for a customer, let's say, who is at 1,000 meters? Okay, if you ask such a question, okay, or sorry, I've given this. Okay, so for 1,000 meters, can you make a prediction? That's the kind of question we are going to ask. You know, that's what we want. Now we want to know what is going to be the value for some unknown value for the x variable, right? So that's what we want to do. I want to first start with a simple assumption. Okay. Assume that you do not know the distance of delivery. Okay. Assume that you do not have any information about the distance of the customer. You only have this 25 times of delivery. If this is the case, what value will you predict for each one of these questions? 100 meters, 1,000 meters, 5,000 meters. It could look like a dumb question, or it could look like a very, what can I say? Kind of a skewed question, dumb question, or very smart question. I do not know. One of these two extreme categories. But what could be the answer?
Roughly for 100 meter, it could be 175 seconds. Well, I mean 175 minutes. Like I'm taking an average, something like 13 minutes takes around 20 minutes. So because of that, 100 would be taking around 175. So I am doing a crude extrapolation.
No, where? See, that is, I do not understand your reasoning.
Sorry.
There's,
Yeah.
but
I interpreted the left one as a distance. Sorry.
That's time again.
Yeah. Got it.
I think we'll have to do a plotting and once we have a sort of a linear chart, or I mean, just a scatter chart, we'll be able to predict better, right?
This is what we have. Now, what would be your answer for each one of these?
Typically, for a longer distance, we will deviate to a higher time, right? Just looking at this data.
The data doesn't have that information. You have only data. Now, think of robots. We cannot think anything. No, we cannot reason out. With the data, what can you tell me?
Okay, so Professor, your question is that I have only the time data. I do not have the distance at all. So which means that I only have y, not the x.
Exactly.
Beyond that.
Exactly. Exactly.
Okay. Okay.
Okay.
That
We can't say anything. Can't predict any data.
Yeah, you can say anything, correct. Okay. But I'm forcing you, you have to use the data.
So for 100 meters, we will take the lower ends of the value. For 1000 meters, we'll take midpoints or the median range of the values. For 5000 meters, we'll take the extreme end of the value, right? Typically, if we have nothing else available.
Okay. Okay. Here is where, okay, in your reasoning, that's a good reasoning actually. That's not bad. But what has happened is you have brought in a bias in your reasoning, namely that our data. I'm going to kill your first name. I'm sorry. How do you say Chuyen or Kuyen?
Oh, sorry, it's Win.
Queen.
But I was just thinking that usually if I got these problems, I would see the distance. I would check the difference between 100 meter and the lowest point and the highest point, and then I would divide it up to the how many times frame here. So there will be so I would take 5,000 meter, minus 100, and then divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so I just get the time frame. So it equals to 400 meter per time frame, but it's kind of biased because it doesn't really take into account the number inside. But,
See, we really do not know anything about distance.
yeah.
When only these numbers are given, okay, for example, all these numbers might have been measured for distances between 10 meters and 50 meters. We do not know that, right? So unless we have that information, we cannot decide to give different answers for each one of them because we do not have distance information.
Question.
Yes.
Is the story narrative still the same? Like, we're not talking about a rocket ship and going to the moon. We're still talking about a store and a person.
Correct.
Okay. Okay. So that's still part of one of the kind of the assumptions behind this. Okay.
Yes.
It gives me a way to guess, start guessing, right? But we don't have the data on the independent variable. So
You are
just guessing.
either you have to guess, okay, in which case you have to make assumptions about what could be the time for 100, what could be the time for 1000, what could be the time for 5000, and you might assume that somehow these delivery times would be related to these numbers, so you have to make a lot of assumptions. So what we have to look for is a very unbiased way of estimating this time. And as far as we know, in our when we have this collection of such numbers, we know only one such thing, namely the average. Okay, as I told you, the average is that number which is being pulled in all directions by everything. Therefore, that's set at the middle level, and that's the most unbiased quantity we can tell. So when we do not have any other information, the only unbiased quantity we can predict or we can give us the answer for these kinds of questions is the average. That is the mean. Everything else will have some kind of bias brought in there. The moment you bring in bias, then you have to explain and justify your assumptions. That's a bigger headache. So what I will do is I will give the same number. Whatever be the average of these numbers, I will give that as the value for time to deliver for 100 meters, time to deliver for 5000 meters, time to deliver for 1000 meters. For each one of them, I will give the same answer. It's a stupid answer. I mean, how can it be the same time for different distances? Yes, But that's the data I have. The data does not support any other answer. Okay. So what I would then do is I will tell whoever gave me this data to get me values for other variables. That's what we will do. But when we are forced to do this, the simplest answer we can give or the most reasonable answer we can give is the average time, which happens to be 22.38 minutes. Okay, we will give the same number for what will be the distance. Okay, so that's like, so somebody mentioned scatter plot. This plot is called the scatter plot. So it's, you can think of this as I have scattered the data on a plot where on the horizontal axis, this is called the x-axis. On the horizontal axis, I have the independent variable, which is the distance. And on the vertical axis, which is called the y-axis, I have the dependent variable, which is the time to deliver in our case, right? So this is how the 25 data points look like. When it's when the data is like this as a tabular column, it might be we were able to get some information, but the moment we plot it on a scatter plot like this, perhaps it becomes much more easier to interpret the data. Okay, I should not say on an average. In general, as the distance increases, the time to deliver also seems to increase. Correct? That comes out very naturally in this data set. Even though, as the other person pointed out, for the first 3 data points, for 36 meters, it's 9.5. For 110 meters, it's 8. For 80, it's 4.88. When we see the scatter plot, that kind of bizarre behavior doesn't seem too bizarre the moment we plot it like a scatter plot, right? It looks like some kind of a general behavior seems to be there, around which there are also these erratic variations, right? That's what it seems like. So now our answer to the earlier question, okay, happens to be this. Whatever be the distance, I will give the same value. 22 point whatever that answer was, right? This red line denotes the answer I would give if I did not have the information about the distance, right? So because this is the mean value of all the y values, okay, this is the answer I would give. Now, obviously, this answer is wrong, or this answer has a lot of errors, right? For this, okay, one more observation. Even with in the tabular column, it was very clear. The last measurement seems like an outlier, right? Because it's very far away from everything else. And when we look at this, can you tell me whether it's an outlier or not? Does this look like an outlier?
Not to me. I mean,
in general, it looks like on the straight line, it seems to fall on the straight line, right? Or some kind of a curve.
But the graph could be an exponential graph.
Yeah. I'm sorry about this. Sorry about this distraction. Extremely sorry about this distraction. Okay, so we have to answer this question. That's another second question I want you to keep in the back of your mind. How do we define outliers for situations like this, right? When we had just one variable we were looking at, now we could draw the box plot and define outlier, as we saw in the last session. But in situations like this, where we want to build a model, can we even define outliers? And if we can, then how do we define? These are the questions we have to work on. Let's keep it in the back of our mind. We'll come to that in a short while. Okay. So that point has for this point, whereas the measured value was something like 79 minutes, our prediction is 22 minutes. So we have this much error in our prediction. Same thing for this much error in our prediction. You could say the same thing for all, you could calculate the errors in prediction for all the data points that we already have, right? Except for this one here, and perhaps for this one here. Every other data point, when we make predictions for those points, using this idea of mean alone, we will have this much error, correct? Now, the obvious question we ask is, we cannot say, let's say we need to get an understanding of how good or bad is our prediction in general, right? So what could we do about that? We could talk about the average error, right? We can say, okay, what is the average error in our prediction? Can you guess what it's going to be? The average error?
Mean of all the errors, sir?
Huh?
Mean of all the errors or no?
Mean of all the errors.
Okay.
Mean of all the errors.
But Rajan, to predict the error, we should have a predicted value, right? I mean,
The value is this 22.88 for every value.
okay.
For every value, I'm predicting 22.88.
Okay.
So what should be the error? What would be the mean error?
Mean error, we will take the difference from the mean and then average it.
This value minus this value.
Yes.
That some quantity. This value minus this value, some quantity, so on and so forth. This value minus this value, this value minus this value, so on and so forth.
And we have three ways of calculation, either an average or a MAD or a RMS.
I'm not doing that. Just tell me the value for the average.
Okay.
What do you expect the value for
And
the
sir,
If we take it's 0, no?
Sir,
It's 0. Why? As we saw, the mean, as we said, is that number which is being pulled equally from every direction. So it's at the equilibrium point.
Yeah, but Rajan, here what we see is there is a slight pull on the negative side by many values, and there is a greater push on the positive value by the outlier. So they will get equated to 0.
Exactly. Exactly. This is what we would find. So
we have to square them.
no.
That's why,
Yes, exactly. So
that's why we have to square them.
exactly. That's right. So since if we just add the mean values, the mean will be 0. So we should not take the errors themselves because they would all add to 0. So we'll have to look at squares. Okay, we'll have to look at the squares. So the way we quantify how good our prediction is, we look at the sum of the squared errors. Not just the sum of the errors. Some of the errors will be 0. So we take sum of the squared errors. Okay. And that's what we use. And in this situation, when we are using the mean value for y, without using any information about the x, whatever errors we get, that is in this diagram, whatever errors we get, that's called sum of squared total errors. That's a name given. Sum of squared total errors. Just remember this, total errors.
Sir,
Yeah.
Another question. I don't mean to try to destroy your example, but we started with an assumption that we don't have the independent or the dependent variables. So how can you calculate that? I'm just wondering how you bridge. What's the bridge between saying we don't have any time
No, we have
associated with
distance values. See, let's go back here, okay?
Yeah. If we could go back.
Okay. So think of the situation where this is the time measured value, and in the next column, I have
Okay,
value.
got it.
Okay. And I'm finding 9 minus 22 point something, 14 minus 22 point something. So these will be negative numbers. But when you come here, 40 minus 22 point something, that will be positive. 35 minus 22 point something, that will be positive. So I'm calculating those numbers. Right?
Okay.
And then I'm squaring them. Let's do this. If you're not convinced, let's do this right away. So I think I have this done already in some previous cohorts. So I'm going to take it from there. So merchants, TikTok, grocery delivery. Okay. So I'm going to move it to the top. So here. So I'm going to save it with today's date, 28. So 326. Okay. So let me create a new sheet here. Okay, this is our oh my god, this might be too big. So I'm going to is it visible now? Clear? Are the numbers clearly visible?
Yes.
Okay.
Yes.
Now, so let's do something here. I'm going to let me introduce one more column here. Say mean, median. So this is all our central tendencies, and then I'll say standard deviation. This is our measures of dispersion. So let's mechanically calculate this average. Mode of these first, this will turn out to be none or 150. Okay, and this is median. These numbers and standard deviation of these numbers. These are formulas I'm using from Excel. So, okay, let it be that way. Let's copy this. So here there is no mode, so it's just a value here. Okay. Now you see the mean is 22.384, mean of the Y value. So what I am saying is Y prediction, okay, no X. I'm predicting Y without using X.
Không có gì tiếng
Fan. Somebody is on the mic. Please mute if you are not talking to me. Thank you. So I'm going to set this equal to prediction is I'm going to give a same value for everybody. Okay, I'm going to give the same value for everybody. Okay, so okay, I'm going to give the same value for everybody. Now let's calculate the error for each person. So for each person, the error is the measured value minus the predicted value. Right? So for some people, it's negative. For some people, it's positive. And let's take the average of these errors. See, it's exactly 0. Okay. So average of errors will always be 0. So this is not a good measure of finding out how well our prediction is. We can say the average error is 0. Therefore, we have great prediction. Nonsense, because theoretically, this is what we are expected to find. So what should we do? There are two things we can do. One is we could do squared error. Okay. So what do? We just square the errors. So everything becomes positive. Right? What is happening? So everything becomes positive. And now if we calculate the average, you see, it's actually a very big number. Okay. Remember, this is square. So if we want to get the estimate of the actual value, then we have to take the square root. Right? So remember that. So approximately we are getting the mean is something like mean error is something like square root of 231, which should be like what about 15 point something, 15 point some minutes is the average error we get. Okay. So this is why we do the square error. And this is called, this quantity, this is called, we'll call it sum of squared totals. Sum of squared total, it's not called totals, it's squared total here. This is what called. So we call it, in short, we call it SST, sum of squared total error. And this is what I have depicted here. This is what I have depicted here. Okay. So measured value minus the mean value for y, whole squared, sum over all measurements. This is called sum of squared totals. Obviously, this is not something good because we have not used the information about the independent variable. If we use the information about the independent variable, what happens? That's the next question. And before that question, we need to ask this, we need to ask another question. We can use this independent variable only if there is evidence that these two variables are related. Right? If these two variables are not related, then you may not even be able to build a model. So, okay, very poor animation. So we ask the question, first question, is the time to deliver related to distance? How can we answer that question? We answer that question using this quantity called correlation coefficient. Okay, we need to figure out what is called correlation coefficient. What is correlation coefficient? The correlation coefficient is formally given by this formula. Okay, this formula might be scary looking with all these different symbols. Remember, I did not tell you earlier, but this is the standard notation that we use. In fact, maybe I have another slide where I describe this. Whenever we have a bar over a variable's name, that means that is the mean of that quantity. So when I have x bar, it means mean of all x values. When I have y bar, that means mean of all y values. Right? Now, when you look at this formula, xi minus x bar divided by sx. What is s? S stands for the standard deviation. No, remember from our earlier class. S stands for standard deviation. So what is it? Value minus mean divided by the standard deviation. You have already seen this quantity somewhere.
This is nothing but the Z value.
Z value, exactly. Okay, this is the Z score or the Z score. This is the standard score. Remember when we talked about comparing apples and oranges, this is what we looked at. Okay, so what is it we are looking at? We are looking at the product of the Z score for the X variable and the Y variable. We look at the product and then take the sum for all values. We have 25 values, measurements. So for each measurement, find this product of the z-scores and then take the mean. Remember, mean is not with respect to the number of measurements, but with respect to the degrees of freedom. Since we have already measured the mean, we lose 1 degree of freedom. Therefore, the mean is always taken with respect to n minus 1. Okay, with respect to n minus 1. Therefore, 1 over. So what we are looking at? We are looking at the average product of the standard scores. What is this product of the standard scores? What does it tell us? Okay, and that's where the key for correlation is. Correlation. Okay, correlation. What is it? Correlation? Are they varying together? That's the question. How much are they varying together? If z-score is positive, does z-score for x, the standard score for x, if it is positive, is the standard score for y also positive on an average? On an average. Or if the standard score for x is positive, is the standard score for y is negative on an average? Okay. Or they move, doesn't matter. Standard score for x is something and standard score for y is doesn't, I cannot predict. So essentially, whatever variation, if I change x, I cannot predict how much change in y happens. That is, on an average, it is 0 for some change in x, or the standard score of the how much x changes when y changes. That's 0 on an average. These possibilities are there. Okay, and that is what is this correlation coefficient measures. Okay. For our data, luckily, the correlation coefficient happens to be 0.9. What does it mean? So let's try to interpret this thing. Okay, I've said do a demo in Excel. Let's do the demo in Excel. Okay, so we'll have to measure the standard scores. So ZX, ZY, we will have to get, right? ZX and ZY. So what is this? This is this value. Let me open parentheses. This value minus mean of x, right? Mean of x, the whole divided by the standard deviation of x, right? That's what is the z-score for x. How about the z-score for y? Same thing, right? The value for y minus the mean for y divided by the standard deviation for y, right? So you see, both are negative. Okay, that's what we are finding in this case. And in some cases, we'll find both to be positive. Here you see, both are positive. Okay, both are positive. Let it be. Now, I told you earlier that the standard scores always have mean to be 0 and standard deviation to be 1. Let's check that numerically, right? So let's calculate these numbers, this average, right? You see, the mean for value for the standard score is 0, the standard deviation is 1. Mean is 0, standard deviation is 1. Now these things don't make sense, so let's not worry about it. Okay. So this I gave you as an exercise if I remember correctly, but anyway, numerically we have a justification here. Now let's calculate the correlation coefficient. What is that? That is nothing but the product of these two standard scores and then the average of those, right? This times this. So average of this ZX, product of ZX and this ZY. Let's calculate the and find the average. In the formula, the average is usually taken as the number of the count. So I'm going to do, actually, manually, I'm going to calculate the average by using the degrees of freedom. With this divided by .90. You see this? 0.90. So let's do something. Let's make everything to be okay. Let it be here. Let it be here. So let's make this. I did not get this. Okay, it doesn't look okay. Anyway, 0.90 is the correlation coefficient for us for this data. No? It's a very simple idea. So we get 0.90. Is it good number or bad number, or what kind of number is this? So here is a little bit of theory on correlation. I'm not going to give the complete understanding. Please take it as an axiom. These are Z scores, correct? And we are looking at average variation together. Okay. So the correlation coefficient, you can show, it is possible to show that the correlation coefficient lies between -1 and +1. Always. Correlation coefficient lies between -1 and +1. Okay. So when the value of correlation coefficient is close to -1 or close to +1, then we say the relationship is strong. When the value of the correlation coefficient is close to 0, then we say the relationship is weak. Okay, it's weak, like shown here. Okay. So this is positive correlation. Perfect positive correlation. This one. The situation we have is something like this: 0.9. Okay, close to 1. Very high positive correlation. So a strong relationship. Positive negative correlation. So as 1 increases, as x increases, y decreases. As x increases, y decreases. Right? But as we get closer and closer to 0, when the correlation coefficient becomes closer and closer to 0, whichever direction, you see lots more variability in the data you can see. When it's 0, you cannot say whether the line is horizontal or vertical or whatever. Okay? So when there is 0, then this is how the data would look like. When the correlation coefficient is 0, we don't have any relationship. Okay. So with this understanding, since we have correlation coefficient to be 0, so 0.9, which is like this, we have very high positive correlation, then we can say that yes, there is a relationship between x and y in our data. Then we ask the question, what is the relationship? Okay. Is this something like this, like a straight line? When I look at this, when I draw this straight line, then immediately it appears to me, you see all these numbers are for in the lower part of the graph, they are slightly above the line. In the middle part, they all seem to be below the line. And then in the upper part, they all seem to be above the line. So it seems like the actual graph might be something curved like this. The actual relationship might be curved like this. Okay. But the moment I draw something like this, another idea occurs to me. Maybe the relationship is something like this. Okay, maybe the relationship is something like this. Okay. So remember, these are all I'm saying is, okay, I know that's a relationship. Okay, I know that's a relationship. Now I am asking the question, is this, which model that should I use? Should I work with this model, or should I work with this model, or should I work with this model, or something more complicated? Okay. And the answer to this question is what is called the Occam's razor principle. What is the Occam's razor principle? We will use this in everything we do. In every model building exercise, we will do this. What is the Occam's razor principle? Yeah.
Sir, can you repeat that again? Outcomes what?
Razor. Blade, Occam's
Razor. Okay.
Okay,
Okay, thank you.
Yeah, Occam's blade, if you want to say a sword. Okay, principle. What this principle states is the simplest answer is almost always the correct and the best answer. Okay, but of course, the simplest answer within your error bounds. Let me correct this. The simplest answer within the bounds of error. Right? Or another easier way to state it is the simplest answer with tolerable errors is almost always the correct answer. It's almost always the correct and the best answer. Okay, this is something we use. And having said that, and again, I'm going to state something of an axiom. I'm not going to go do any mathematics or give any justification. I'm just going to state it as an axiom, namely, the way we calculate the correlation coefficient. Okay, the way we calculate this correlation coefficient. This is called linear correlation coefficient. Okay, what does it mean? This correlation coefficient, when it's very strong, it actually tells us that this kind of a relationship, a straight line relationship, no, we can find a strong straight line relationship. That's what it tells us. Okay, that's what the correlation coefficient tells us. So when the correlation coefficient is high, we will use a linear model. If you are not justified with this, if the linear model provides results within your tolerable errors, that is according to the Occam's razor principle, then we will go ahead and use a linear model. Okay, we'll go ahead and use a linear model. Okay. So with this idea, okay, for this data, since the correlation coefficient happens to be 0.9, which happens to be close to 1, we will say we will find a straight line. Okay, so which straight line? Okay, so there could be infinity of straight lines, right? We can come up with which of these straight lines is the actual straight line we will use for making predictions. That is the question of learning. That is the question of fitting the model or identifying the model, identifying the straight line that gives the best predictions. Okay, what can we say? How can we quantify the best predictions? The best predictions are those predictions which have the least error. So we are going back to the idea of error like before. Okay, so yeah, here is this. Maybe this slide should have come earlier. So a simple note on notation. Bar over a variable name means y bar. It's a mean value. Hat over a variable name denotes a predicted value. From now on, we are going to see this hat. I think we saw that No, we didn't see that earlier. Now we are going to see this. The predicted value. Okay. If the predicted value, we denote by the symbol hat. Hat over the variable name. A bar over the variable name means the average or the mean value. Okay. So again, a little bit of note on terminology, a reminder. So the Y variable is called the outcome variable, the target variable, the predicted variable, or the dependent variable. The X variable is called the predictor variable, regressor variable, or the independent variable. Okay. Sometimes we will say the regressor variable. Sometimes we will say the predictor variable. Okay. Sometimes we use the terms like features or dimensions, but all these denote the X, and outcome, target, predicted, dependent, all these terms denote Y. Okay. Okay. So I said we will have a straight line model. So mathematically, a straight line is denoted by this equation. Okay. So this is, you are probably familiar with this equation in a different notation. We might have written something like y is equal to mx plus c. This is the standard format that this is, in fact, is a universal notations people use when they introduce linear equations. In our high school first course in calculus or first course in linear algebra or geometry, linear geometry, no?
Managerial accounting.
Say it again.
Managerial accounting, fixed cost plus your variable cost structure.
I'm not seeing you.
I was just using like a graph we used to see, right? With your kind of like your fixed cost or your cost structure with a constant, say, a value, and then, but I'm not sure if it's the same thing, but your costs go up, say, by 50% times,
Yes.
you know, whatever value your units are, let's say.
Exactly. It's the same thing. It's the
Costs
same.
in units.
Yes. It's the same thing. Okay. So here's the best fit line, let us say. Okay. Now, what happens? This is the measured value, yi, denoted by the symbol yi. And here we have the predicted value, yi hat. Okay. Now, remember earlier, our predicted value was somewhere here, around 22, it was constant, 22 point something. Okay. So we had a large error earlier. Now the error has decreased. Right? The error has decreased. So the error we have is this much. Yi minus yi hat. Actually, this should be the other way around. The arrow should be the other way around. Okay. Yeah, from here to, okay, yi minus yi hat. This is how we denote error. Okay, fine. Okay, yi minus yi hat. Okay. Here's the error for this point. The error for the other point, so on and so forth. Okay. Using similar ideas now, again you will see positive errors and negative errors. On an average, they will cancel out each other. Therefore, sum of errors will be only 0. Therefore, to quantify how good our model is, we have to use sum of squared errors. Sum of squared errors. These are the errors that are still present in spite of the best model we get. In spite of the best model we get. Therefore, these errors are called residual errors. These are called residual errors. They are still there in spite of the best model. So we say sum of squared errors, we use the symbol SSE. sum of squared errors. Some people say sum of squared residual errors. Okay, but we always use the symbol SE, sum of squared errors. Okay, given like this: yi minus yi hat, the whole square. Okay. Okay. This is called the model that we are going to have. The model, there are so many lines, right? The line that we are going to work with is that line which has the lowest value for this SSE, sum of squared errors. The line with the lowest sum of squared errors is the line that we will use as our model. What does it mean? We need to find that where those values of beta naught and beta 1, that particular pair of beta naught and beta 1 values that gives the lowest value for sum of squared errors. Once we find those values of beta naught and beta 1, we say that we have fixed the model, or the learning has happened. Okay, the learning has happened, or we have fixed the model when we have that values for beta naught and beta 1 that result in the lowest value for the sum of squared errors. Okay, that's what learning is all about. This is what supervised learning is all about. Where is supervised learning? yi is already present here. yi is present, right? So your value is already there, and yi hat is the prediction. So we want to see how good your prediction is in comparison to the actual value. Therefore, this is supervised learning. Okay, this is supervised learning. Okay, let's finish this, and then we'll take a. Yeah.
Why is this squared? Why is not like cube?
Say it again.
Why is it sum of squares and not sum of cube?
When you take cube again, what would happen? Cube, if some value is negative, or cube of a negative number is again a cubed value. Cube of a positive number is a positive value. Therefore, it could, they will cancel out. Right? You could take the fourth power. Yes, of course you can take the fourth power. Fourth power of negative number is positive. Fourth power of positive number is again positive. But why do you want to do that when using Occam's razor principle? The square does the same task for you.
Right.
Okay. So we would do the sum of squared errors. We would stick to that. Okay.
Okay.
And added to that, there are other interpretations. In statistics, these are called moments. Okay. First moment. Just the absolute difference is the first moment. Squared difference is the second moment. Cubed difference is called the third moment, fourth moment, fifth moment. Each one gives different kind of statistical information about the data. Okay. For example, sum of squared errors gives the spread of information about the spread of the data. Okay. Then cube gives you an information about something called the skewness of the data. Fourth power gives you something called the kurtosis. Okay, how the skewness itself is varying over the data. So they give different information. Since we are interested in how good the variation of the errors is, the errors should vary within a small region. Okay. Therefore, we should restrict only to sum of squared errors. So there are multiple other. Yes, Atif Mir, please go ahead.
You briefly mentioned how this equation represents supervised learning. I'm trying to conceptualize it. Can you give us, I know this is an example itself, but how would it be different from unsupervised? Maybe that will help me understand better.
In the unsupervised learning, yi will not be present, right? In which case, we will not even use this quantity. We will have to use some other quantity to do the task.
Can you give me an example of that where y is not present?
Give me an example of when y will not be used, right? Okay.
Yeah.
So let us say you okay. I worked on this problem recently where I wanted to forecast the values for a few SKUs. Okay. And it's a few, I'm talking in terms of a couple of thousands of SKUs. Okay. And when we wanted to do this, when you want to forecast, I want to build a model like this. Okay. So I have historical value. I build a model, compare against historical value to see how good the model is. There, I will use my yi, which is already measured. That becomes my supervised learning. But the task was, the data was so erratic, we couldn't get any usable model. So what it did was, okay, let's not worry about the y value. What is the y value? Total sales. Okay, let's not worry about the y value. Let's look at, are there any products that are similar? Can we combine products? Okay, say for example, different types of nuts, different types of bolts, different types of plates. Okay, so can I combine all the plates together as one group and then build one model for all the plates together? I do not, from the data, I do not know whether they are plates or nuts or bolts or what. So there, I did unsupervised learning. Segregate this data into 12 groups, okay? And then for each group, I build the model separately. And that is an unsupervised learning, where we are not using Y. We are not using the sales value at all. We are using the other inherent characteristics of the object itself. Right?
Right. So conceptually, I'll just simplify it so I make sure I understand it. So if we collect data, for example, climate or anything with thousands of columns on Excel, and we don't know how to visualize it as because our minds cannot capture that complexity.
Correct, very correct.
Okay, we'll just run the model and see if it spits out any patterns.
Correct.
Okay, thank you, sir.
So I'm going to do some mathematics. If this is something that you have not done for a long time, or in layman's term, if this goes over your head, that's okay. You are not going to lose much. But the last few points, I would like you to pay attention to. Okay. So this is the sum of squared errors. Predicted value is given by this linear model. Therefore, I can, in the predicted error value here, I can write beta naught and beta 1x. So I could write it like this, sum of squared errors. Okay. Now, what did I say? I said that I want to find the value for beta naught and beta 1 such that my sum of squared errors is the minimum, the least value. So if the word minimum rings a bell, and if you can relate it to calculus that you studied in your college days, and if you can remember the calculus of maxima and minima, okay, then you could immediately recollect that all you are trying to do is take the derivative of this sum of squared errors with respect to beta 1, set it equal to 0. Likewise, take the derivative of the sum of squared errors with respect to beta naught and set it equal to 0. Okay, this is the process of minimization. Okay, so now what we will do is this will result in one equation. This will result in another equation. We have two equations in two unknowns. What are the two unknowns? Beta naught and beta 1. These are the two unknowns, two equations, and then we can solve for these two variables. And when you solve, okay, I'm going to give you the answer straight away. I'm not going to show you the solution. I'm going to give you the answer like this. Beta naught is given by this expression, y bar minus beta 1 x bar, where beta 1 is given by this expression. So let's focus on beta 1 first. Okay, it's very easy. Look at this equation. As the other gentleman said, this beta 1 tells us how much does y change for a unit change in x, right? Folks, I'm sorry, I have to take a break now. So we will come back to this in 10 minutes time. Let's take a break. The time now is 8:04 on my watch. Let's take a break. 8:15 we will meet. Okay. Sorry about this. Let's take a break now. Thank you. Hi, everyone. I'm sorry for just cutting off in the middle and disappearing like that. I had, ironically, I had a grocery delivery happening at my home, and there was nobody else, so I had to go take care of that. I'm sorry about that. But it was a very funny coincidence. Anyway,
Did you get the time and the distance?
unfortunately, not. I didn't have time to talk to him. Okay. So, okay, actually, I asked him. This is something very interesting happening in cities like Chennai. I'm sure that happens in other places too, where it gets very hot as the summer approaches. Right? Chennai city is it's a coastal city, so it becomes very humid. The humidity sometimes in summer reaches 90% and even sometimes saturates. So it's very it gets very hot. And so what happens is during the peak summer, even the government declares no work window during the peak summer time, which usually happens sometime in May. Okay, for 3 weeks in from the beginning of May till the third or fourth week of May. Usually it's called the no company can have workers working outdoors during I think from somewhere from 11 a.m. till about 4 p.m. or something. You could have your workers work before that and after 4 p.m. So it gets that uncomfortable. And the delivery companies also, this big delivery, this big online groceries and online stores, they have a similar practice. So they bunch all their deliveries very early in the morning or very late in the evening. So most of these people don't serve during the daytime, between 10 to 4 or 10 to 5. So this kind of disruption is going to happen for the next 2-3 months in the city where I live. But of course, I think it's a humane practice. So that's what I was talking to him. And he said, like everybody else, he says, life has to go on. So we do this. We would also like to be back home in the evening, but this is the easiest way to manage this kind of task. Unfortunately, I did not ask him where he was coming from, nor how much time he took. This is another thing. For example, this in real data, what happens is this: even if we measure, I'm sure these companies keep track of the times to deliver because they always do the when they start when they pick up the delivery the items to deliver, they punch in, and then their punch out time is when they get the OTP from us. The customer has to share a code saying that the delivery has been made. So that's what they use as the delivery time. And I'm sure they use this information to optimize their processes. And I'm sure what they do is they bunch deliveries to a locality. So you would see the distances would all be identical. But of course, how these delivery persons, they choose to deliver, which unit they choose to deliver first, and second, the times would vary, right? So that's another interesting detail we will be seeing in real data, but of course not in this data that we have. Coming back to our problem, these two parameters, the most important parameter is beta 1, which essentially tells you how much the y variable changes for a unit change in the independent variable x, right? So essentially change in y divided by change in x. Statistically, change in y is denoted by the standard deviation, change in x is denoted by the standard deviation in x. So beta should be something like standard deviation in y divided by standard deviation in x. However, these two standard deviations, these two variations are modulated by the correlation coefficient. Therefore, beta 1 happens to be this formula. So this is very easy to remember for a model like this. Once we have the beta 1, the constant beta naught can be calculated using y bar minus beta 1 x bar. This kind of deriving the formula is easy when we have only one variable. But the moment we add new variables, like for example, like other variables we discussed, the weight, the load of the delivery that's being made, the traffic conditions, that would be a categorical variable, the duration, the time slot during which the delivery is being made, whether the unit is in the ground floor or in upper floor, all these different variables when you put in, technically, it is possible to derive formulas like this. It is possible, but very tedious and very difficult. The moment you put even two variables, this becomes very tedious. Okay. So what people do? People use, am I talking that somewhere here? Let me see. No, I'm not talking that here. So people use numerical methods. Okay. We don't use such formula, but rather we use numerical methods. What do we mean by numerical methods? This is the usual idea. Okay, the numerical method is usual idea is we start with a guess value for beta naught and beta 1. Okay, let's say we start with a value of 0 and 1. Okay. Then with those values, we make predictions for each of the data points, calculate the sum of squared errors. Okay, keep it. Then we change the values of beta naught and beta 1 slightly, by a very small number. And then redo this calculation. See whether your sum of squared errors decreases or increases. If it decreases, then we know the original guess was not the optimal guess, because now a different value gives a lower sum of squared errors. We do not know whether this is optimum. So what we do? We change this again. We change beta naught and beta 1 again. Okay? And calculate a new value for sum of squared errors. See whether it's decreased or increased. If it's decreased, then discard the earlier value and repeat the process until it starts increasing. Okay? So we started with some value, guess value for beta naught and beta 1, and keep changing it as long as the sum of squared errors keeps decreasing. The moment it starts increasing, you step back and use the previous value where you had the lowest sum of squared errors. Okay, lowest sum of squared errors. And that is called numerical method. So the conceptually, this is a very simple idea. But there is one small nuance. There are two questions we need to ask. Okay. Okay. I started with some random value for beta naught and beta 1. That's correct. I'm going to change the values of beta naught and beta 1. That's correct. How much should I change it by? Okay. Should I change it by 1%, 0.1%, or should I change it by a fixed number like 10, 1, or 0.001? No, that's called the step size. In our parlance, that's called the learning rate. The learning rate. How much should I change the values of this beta naught and beta 1 so that I go to the minimum? Okay, this is called the learning rate or the step size. This is the first question. You don't have an answer to this. We don't have true answer to this. What you have to do is you have to play with different numbers and then come up with an optimal value for that. Okay. The second question is, should I increase the values of beta naught and beta 1 or should I decrease? So the magnitude of change and the direction of change. Okay. These are two important questions. Luckily for us, there is a technique called gradient descent. It's a technique called gradient descent. We will look at this technique in a future session. There's this technique called gradient descent, which will tell us the direction of change. Should we increase the value or should we decrease the value? That this technique, gradient descent, will tell us. How much should I increase or how much should I decrease? That amount of variation, that magnitude of variation is left to us. Is left to us. Okay. And therefore, that learning rate, fixing the learning rate, is a separate problem. Usually, for linear regression problems like this, people start with a standard value of 0.001. Okay. What is the point of, why is the learning rate very important? Let's think about it. Let's think about it. That assuming that the initial guess values of beta naught and beta 1 are different from the optimal value. Okay. If you have a big learning rate, okay, what could happen? It is highly possible that you might miss the optimal value. Let us say the optimal value is 3.75. Okay. You are starting with a value of 1. Okay. Let's for beta naught, let's say for beta naught. You are starting with a value of 1. The optimal value happens to be 3.75, let us say. If you use a value step size of 1, then what would happen? 1, 2, 3, 4. You have missed the minimum. Right? So large step size, we might very easily miss the minimum. Even if a step size of 0.1, let's say, we take, then we will do 1, 2, 3, 1, 1.1, 1.2, 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.7, 3.8. So 3.75, we still miss the minimum. So we need to take a small step size. But if you take a small step size, let us say very small step size, 0.001 in this case, okay, then what will happen? You start with 1, 1.001, 1.002, 1.003. You will take 1,000, 2,000, 3,000, 3,750 steps to reach the minimum. Okay, large number of steps. So it will take a long time to reach the minimum. So you have to somehow use some heuristics or try out these different things, okay, and then arrive at the optimal step size. For example, in this example, 0.01 would be the optimal step size. Even when you start with 1, okay, we come to 3.7, 3.71, 3.72, 3.73, 3.74, 3.75, we will reach the minimum. Right? So getting the step size is a very, very difficult problem. How do people tackle this? Okay, people tackle this with two techniques. One is you keep a threshold on the error, tolerable error. Okay, I need to have the minimum error, but I do not know whether I will reach the minimum or not. But if the error is, if the change in the error, the first previous value, the error was this much. The next iteration, the error is this much. If the change in error, the change in sum of squared errors if it is less than some number, let us say 0.001, okay, then I don't care. I'm not worried. I will consider all of them to be equal. So I'll stop. So when the change in the error is less than my tolerance for this change, then I will stop. That's one criterion you can use. Another criterion is whatever it be, okay, if I have used 100 iterations, I'll stop. I need to reach this tolerable change in error or the minimum within 100 iterations or 1000 iterations, something like that. So you use these two steps with these two ideas, number of iterations and the tolerable change in the error, for you to identify what is the minimum value. Let's say you have reached one of this, you have reached the number of iterations. You are breaking this minimization because you have reached the maximum number of iterations. Then you already know that you have not reached the minimum. Okay. Therefore, you may probably have to increase the step size. Okay. But then you have reached the maximum number of iterations, and still your difference in the error, the change in the error is still big. Then it means you have a large step size, so you have to reduce the step size. So you play with these ideas and try to come up with a good method to reach this. Direction of change, gradient design will tell. The amount of change, that is fixing the learning rate. This is called hyperparameter tuning. We'll learn about what is hyperparameter in a short while. It's called hyperparameter tuning, and that is something we have to play around with. Okay. So with this, what we'll do is we will assume that we will not use any of these formulas to calculate, but we will only use the numerical method. We will use the numerical methods to fix the model. And what is meant by learning? Learning is arriving at the values of beta naught and beta 1, such that we have the least sum of squared errors. Okay, that's what is called learning. So what is the process of learning? The change in beta naught, beta 1 values numerically, right? Using gradient descent and using the learning rate that we have, keep changing the values of beta naught and beta 1 such that the error becomes minimum. And that process is called learning. And once you have reached the minimum, then we say the model has been learned. Yes, John Sirani, please go ahead.
Rajan, so why we have to use numerical method? If we use this formula itself, we cannot identify the best optimal value.
Yes, you can. You can, and you will. You will identify. But remember, this formula is valid only for the case where you have only one variable.
Yes, that's true.
The
Yeah.
moment you go to two variables, two independent variables, the formula deriving the formula becomes difficult. Okay? In real situations, we would have few dozen variables.
Got it. Yeah.
Where we cannot do this, we have to resort to numerical methods. Okay.
Got it.
Okay. So this is what we had earlier. This is the sum of squared totals. Okay. Now we have the model. We have sum of squared errors. Okay. Now, so this sum of squared errors. Where does the word regression come from? If I remove the model, the residual errors go back to the total errors by this amount. The residual errors go back to the total errors by this amount. Right? So these errors are called regression, going backwards. Regression. That's where the model regression comes. The word regression comes from. So this is called the regression errors. Okay. If I remove the model, how much more error would be introduced such that I go back to the total errors. That is called the sum of squared regression. These are called regression errors. This is called SSR. SSR stands for regression. SSE stands for residual. Even though both start with R and R, we use SSR for regression, SSE for residual errors. Okay, so 3 types of sum of squared errors. Okay, why? Because there is some wonderful mathematics among these 3. Okay, I'm giving this here. You don't have to worry about this. The mathematics that is important to us is, okay, these are also called total errors. These errors, that is the residual errors, are also called unexplained errors, because those errors, that much error is still not rectified by the model. It's still not rectified by the model. So these errors are still unexplained. But these regression errors are have been rectified by the model. So we call them explained errors. The model explains these errors. Okay, that's a term we use. It's a different name. Total errors, residual errors, regression errors. Total errors, unexplained errors, explained errors. Okay, and this is the mathematics. In the squared sense, total errors is equal to unexplained errors plus explained errors. Total errors is equal to unexplained errors plus explained errors. Yeah, unexplained errors plus explained errors. Okay. I'm sorry, folks. You have to excuse me once again. There is somebody ringing a bell in my place. Give me just 1 minute, please. Thank you. Thank you for your patience. I'm sorry, this is an unfortunate situation. I apologize for these disruptions. For the next 30 minutes, there won't be any disruptions, I hope. Okay. So let's continue with this. There's also the other term people use, leftover errors, essentially meaning residual errors. No, residual is a leftover, and then rectified errors. Same name. So in the squared sense, total errors is equal to, that is, sum of square totals is equal to sum of squared errors or sum of squared residual errors plus sum of squared regression errors. Remember that. Okay, this picture should be, you should have this picture in your mind, so things will be clear. Of course, you have the slides with you. You can also use that. Now, very occasionally, and this will not happen in simple linear regression. What is simple linear regression? Simple linear regression is when we have only one variable, only one independent variable, like our example now. But in some cases, it is possible. Imagine a situation where for this data, for this kind of a data, you end up with a model that's like this yellow line. Okay, not like this blue line, but like this yellow line, let's say. If you end up with a model like that, okay, of course, our mathematics tells us that it will not happen. But numerical calculations can give you anything. Okay, not anything. Occasionally, this is a very rare event. But in very rare events, it could happen. When it happens like this, okay, what happens? You see, your residual error is bigger than the total error, right? Your residual error, that is the measured value minus the value predicted by the model, is bigger than the total error. That is the measured value minus the mean value. Okay. If that happens, what could happen? Okay. The leftover errors, the residual errors, is bigger than the total errors. That means the rectified error, okay, the sum of squared regression errors has to be negative. Has to be negative, right? Can this happen? That doesn't make sense. Okay, but remember, very occasionally, especially when you have complicated situations, and when the model is not able to accurately understand the nuance in the data, this could happen occasionally. Very rare, but it could happen. So we will see what is the effect of something like this happening. Okay, so reiterating once again, total errors in the squared sense is equal to the sum of unexplained errors and the explained errors. That is, sum of squared totals is equal to sum of squared errors. SST is equal to SSE plus SSR. A little bit of mathematics. I'm going to divide everything by, okay, I'm going to bring the sum of squared regression on this side, on the one side. That will be equal to sum of squared totals minus sum of squared residuals. Now I divide everything by sum of squared totals. Sum of squared regression or sum of squared totals is equal to sum of squared totals by sum of squared totals minus sum of squared residuals by sum of squared totals. This fraction is 1. This fraction is 1. Right? Therefore, sum of squared, this fraction, let's look at this fraction on the left hand side. Sum of squared regression over sum of squared totals. We give it a symbol R squared, capital R squared. Let's look at the meaning of this. What is it? This is nothing but the proportion of the total squared error, squared total errors. What proportion of the squared total errors is the regression error? Correct? That's what it is. It's a proportion. What proportion of the squared total error is the squared regression error? And that proportion is called R squared. Now let's look at this number. Okay. Regression. Okay. That is this explained error. Okay. If the model is a good model, then this explained error should be close to total errors. Almost all the error must be explained by the model. If that is the case, it's a good model, right? That is, if this number R squared is close to 1, then we have a good model. If on the other hand, explained error is a very small proportion, since all of these are positive, this has to be a number. Numerator is positive, denominator is positive, therefore this can be only a positive number. Okay, therefore that's what we are thinking. We'll come to that. We'll come to the weird situation later. Okay, this when this sum of squared errors is a small proportion, then R squared is close to 0. So R squared varies from 0 to 1 And when the R squared value is close to 1, we have a good model. When R squared is close to 0, we have not so a good model. Okay. So this R squared, this is called the regression coefficient. This is called the regression coefficient. So this is very important. Okay. This also you can see R squared is equal to 1 minus SSE over SST. So usually we do not, we calculate the sum of squared errors. This is easy to calculate, right? Because you have calculated the model, predicted value, and measured value. This is very easily calculated. And sum of squared totals, mean value, measured value. This is also easily calculated. Therefore, R squared is usually given by this number. Is usually determined by this number, 1 minus SSE over SST. Okay. So in very weird situations, say for example, when SSE is very close to SST, okay, so this R squared will be close to 0. And if you have some floating point errors in your calculations, then this could turn out to be negative. Okay, so occasionally R squared can turn out to be negative. If you get R squared to be negative, please take a look at, first thing you will have to resolve, you have to diagnose whether your algorithm is doing something meaningful in terms of floating point calculations or using good correct software. If you are convinced that your calculations are correct, then go look at your model. Perhaps your model is missing some variables. That's usually the case. Okay, so in summary, for reasonable models, for almost all good models, sum of squared errors is always less than or equal to sum of squared totals. Therefore, R squared lies between 0 and 1. R squared is a proportion of total errors, squared total errors, that is explained by the model. Okay, sum of squared total errors that is explained by the model. What proportion of the sum of squared total errors is explained by the model? That's called R squared. People sometimes say this is the variance in the data that is being explained by the model. That's what people also say. Okay, which is another correct way of saying it. R squared close to 0 implies a poor model. R squared close to 1 implies a decent or good model. Okay, so now, more than the sum, a better metric obviously would be the mean. Using the mean would be a better metric. And using the mean becomes much more meaningful when we have more than one independent variable. Okay. Therefore, what we are going to do is, instead of using sum of squared errors, we are going to look at mean of squared errors. Mean of squared total errors, mean of squared residual errors, mean of squared regression errors. Okay. When we look at that, then how do we calculate the mean? The mean we have to calculate by dividing the sum by the degrees of freedom. Okay, by the degrees of freedom. Right. Now let's look at the sum of squared totals. Okay. How do we calculate degrees of freedom for sum of squared errors and sum of squared totals? Okay. For getting the sum of squared totals is nothing but y minus y bar. That's all. Right. Therefore, we are losing 1 degree of freedom. Therefore, the degrees of freedom for sum of squared totals will be number of data points minus 1. Let's think about this. Yes, correct. Okay. On the other hand, let's look at sum of squared errors. How did we get that? sum of squared errors. Already 1 degree of freedom lost when we are calculating the mean. Then we build the model. When we build the model, we calculate two quantities, beta naught and beta 1. Two quantities, right? Therefore, for this, for the numerator, we lose totally 3 degrees of freedom. Right? We lose 3 degrees of freedom. Okay. N minus K, where K is the number of parameters. In our case, the number of parameters is 2 minus 1. Right? That's the number of degrees of freedom for the residual errors. So using this degrees of freedom, using this formula, we get a new value for the R squared. This value for the R squared is called adjusted R squared value. What is adjusted? It is adjusted for the degrees of freedom. It is adjusted for the degrees of freedom. So whenever possible, we have to look at the adjusted degrees, adjusted R squared values, not the R squared values. Okay. All software will give you both R squared and adjusted R squared values. By default, we will stick to adjusted R squared values. Okay. Because why? These are adjusted for the degrees of freedom. Yes, John Sirani, please go ahead.
Yes, in this case, we have any limitation for this degrees of freedom, or that is also a continuous number actually?
No, degrees of freedom is how many we have. Let's say in your model, let's say you have 3 independent variables. Then you have 4 parameters: beta naught, beta 1, beta 2, beta 3. 3 coefficients and 1 constant. Okay. Therefore, this becomes 4.
Okay.
Okay. So it will be n minus 4 minus 1. So it will be n minus 5 in that situation. Now here is a caveat. Here is a catch here. Okay. Let us say you have 25 variables and your data set, the data size is also 25. Okay. So what will happen? N is 25 minus 1. You already have minus 1, that means 24. Now you have K. K is 25. 24 minus 25 minus 1. So sum of squared errors becomes, this mean squared errors become negative. Mean squared error now becomes negative. So this kind of adjustment is applicable only when you have a large data set or the number of features is small compared to the data set. Okay, that's one constraint we have got to work with. But otherwise, this is whatever number we get. Okay, so I have given myself an instruction, do a demo in Excel grocery delivery. Let's do that. Okay, let's do that. This is what we have, right? So we have X, Y, all these things are there. Let's use the formula. Now we know that since it's only one variable, let's use the formula and calculate beta naught and beta 1. Okay, so let's do this. So beta naught, beta 1 we'll calculate first, and then we will calculate beta naught. Okay, because that's what we had, right? So this is what this is equal. This is rho times sy over sx. Correct. This is what we had, and this is equal to y bar minus beta 1 times x bar. Okay, what is y bar? Mean of y. X bar is mean of x. So on and so forth. Right. So let's calculate this. So beta naught, beta 1 is equal to rho. We already calculated rho. What is rho? The correlation coefficient times what is sy? Sy is the measured value, standard deviation for the y variable, which is this. divided by Sx, which is the standard deviation for the x variable, which is this. So we have the beta 1 value, okay, in the model. What is the model we are working on? Okay, let me let's put it here. So what is the model? The model we are working on is y hat is equal to beta naught plus beta 1 times x. That's the model we are working with, right? So beta 1 is here. What is beta naught? Beta naught is equal to y bar. What is y bar? Average y minus beta 1. Here is beta 1 times x bar. Average x. Okay. So this is what we have. Okay. So let's write the equation. What is the equation? Time to deliver is equal to 4.85 minutes plus 0.04. Sorry, let me do this. 4.85 plus 0.0433 times distance. Okay. So this is the equation we have. 4.84. Okay, 8450. 4 digits will have. Okay, 8450 plus 0.0433 times distance. So this is the best model for our data. Okay. So what should be the predicted value? Y hat. Y hat now, what should we have? We have to use this equation. Is equal to 4.8450, or we can just say beta naught plus beta 1 times the distance, which is x. Okay. So this is what we have. Right. So let's calculate this all the way. This. Right. Yeah. So we have the predicted value y hat here. Okay. Let's compare it with y measured. No, this is y hat. So y measured. Let me copy and paste this. So if you see, for some of them under prediction, for some of them over prediction, we have something like this. So some positive, negative errors. So let's calculate y hat. So y are errors, residual errors. So what will be the residual errors? Residual errors will be y minus y hat. Right? So blue minus red, right? So residual error we can calculate like this. Then you can square, add the mode, mean, whatever you can do. Okay. So that way you can calculate the R squared value. Okay, R squared value. I'm going to show in all software like this. I'm just showing you what it is. Now they are just hands on. Now, in all software, of course, all these things are automated. You don't have to manually do this. You can actually go and ask the software to do. So, for example, I'm using LibreOffice. I'm not using Excel, but there are similar things. You go for data tab, and then in the data tab, search for statistics. Okay, and then you should be able to find regression in there. Here I'm going to data statistics and then regression. Okay, so I will ask, what is the independent variable? What is the independent variable? That is x values, right? I'm going to use this x value, including the label, and it's going to ask me dependent variable. What is the y value? So I'm going to use this y value. Okay, and I'm going to say yes. I have selected the labels also. Where do you want to print the results? I want to print the results, let us say here, some cell, I'm choosing a cell, okay? And then if you see here, it gives you something called confidence level, okay? The confidence level is nothing but, remember the alpha I mentioned when we were talking about hypothesis testing, that is 0.05, 2.5% here, 2.5% here, so 0.05, okay? 1 minus alpha is called the confidence interval or confidence level, okay? And what we do is, we'll check this confidence. If you want, you can change this, okay? Or let's choose the standard confidence level of 0.95, which translates to alpha of 0.05, okay? And I'm not clicking any of these check boxes here. I'm choosing linear regression. Of course, this has something called logarithmic regression. This has something called power regression. I don't want it. I'm doing only linear regression. So we'll do linear regression and then go ahead and click OK. Okay. Before we can clear, do a what is called blink. Before we can blink, the results are here, and you can see that we'll look at each one. Okay, we look at. Oh my God! Look at all these values. Do format cells. We have 4 decimal places. Okay. In fact, we can do that for everything. Okay. Now, there are multiple things you would see here. Okay. I'm just first going to focus on this thing here called, you see something called coefficients, and then something called here the intercept and x. The name intercept is nothing but this is beta naught. Okay. It says. And this is nothing but our beta 1. Okay, here, go here, right? So, here, I do says X, I won't say beta 1. You can see that the value is 0.0433. That's what we calculated earlier. 0.0433. Remember this 0.0433. And for beta naught, 4.845. Let's check what happens. 4.8450. Okay. So this is where the model is output here. So I'll give the name model here. Model. And there are a few other things. We'll come to that in a short while. Now, if you go to the top, okay, what kind of model it is? A linear model. Okay. And if you see here, it gives something called regression statistics. And you see R squared. It has calculated R squared, 1 minus SSC over SST. It's calculated that. And it has given this number. It has also calculated adjusted R squared and given that number. They are very similar. 8180. That's all. Okay. Now, approximately both are, I'm going to say 81. R squared is 81. Now, I want you to pay close attention to this number 81 R squared value and the correlation coefficient value. Do you see some connection? Okay, let me write here correlation coefficient that is 0.90. And let's see, is equal to this number. Okay, R squared value is equal to this number here. Okay, do you see any relationship between these two?
They are
Oh, so
within
one-
one of each other.
Square of
Say it again.
it appears to be a 0.81 appears to be the square of 0.9.
Exactly. It is. In fact, we can check it out. Okay. Let me see here. Might have some. Okay. Okay. Is there? What is here? And it says it's line estimate. Okay. It's actually the number. Okay. So it is exactly correct. So R squared value, R squared is equal to rho squared for simple linear regression. Okay, that is for a simple linear regression. What is simple linear regression? Regression with one independent variable. For that, R squared value is rho squared. Okay, that happens to be the mathematics. Okay, the meaning we came from this was something different. The meaning, the way we came to that R squared was different. But mathematics shows that R squared is equal to rho squared. Okay, now, so even before we do the modeling, we could check by squaring the correlation coefficient value, we would get what will be the R squared value. And if the R squared value is poor, let us say if you have a correlation coefficient of, let us say 0.65. Okay, so if it's 0.65, the rho value is 0.65, correlation coefficient. Therefore, R squared will be 0.4225. Is it a good number for you or not? You make a call. You make a call. Okay. If it is a good number, well and good. If you are not happy with this number, then you are not going to get a good model. You already know. Okay, you already know beforehand. Okay. For a simple linear regression, this is a massive time-saving exercise. Okay, let that be there. If you see here, that is these things will also output something called before that, let me do one thing. Alpha. Let me is 1 minus confluence. Okay. They also output something called analysis of variance. Okay. The model is not the correct thing. Let's call it parameters. Okay, parameters. Or maybe model parameters. So analysis of variance. I'm not, I mean, that's the actually true meaning, but I'm also going to call it model diagnostics. Model diagnostic. I'm going to call it first step. Yeah, I'm going to call it analysis of variance. I'm going to call it model diagnostics first step. What does it do? It calculates, if you see, it calculates regression, sum of squared. So this is the sum of squared regression. Okay. Residual, sum of squared residual errors. That is SSE, and this is SSR. The corresponding degrees of freedom. Okay. So it calculates something called the mean sum of squared regression, mean squared, not mean sum of, mean squared regression, mean squared residual. Okay. And if you see here, there's something called F. Okay. And this F is equal to this mean squared regression over mean squared residual. Okay, mean squared regression over mean squared residual. It calculates this quantity. This quantity is called F. Okay. Now, what is this F? Remember, we studied normal distribution. Okay, I know we are already 9:15 or 2 hours 45 minutes. So bear with me for another 5 minutes. We will understand this output and then we'll call it a day today. Okay. And when we come back, there are a few more very exciting things we will do next Saturday. Okay. Of course, the slides have those details, but we'll go through them next Saturday, one by one. Okay, here's the thing. Remember, we had the normal distribution, right? And then we said the alpha. And then we said if anything, if we hypothesized for the mean value, and if the measured value is in the reject regions, that is 2.5 on this side, 2.5 on that side, if it's beyond those, then we reject the null hypothesis, right? Likewise, there is something called the F distribution. Okay, there is something called the F distribution. The F distribution, what it does is it compares two variances. Here you see these are the two variances total, right? The regression. Regression is something minus something the whole square divided by the degrees of freedom. That's some kind of a variance. This is residual. Again, this is some kind of variance, right? So we compare the two variances. Okay, and that how do we compare? The larger number goes in the numerator, the smaller number goes in the denominator. F definition is that. F definition is that. Okay, larger number usually is a regression. Regression goes in the numerator, residual goes in the denominator. Okay, that's what F definition is. Now, what we can do is this F is actually this like how Z score has a normal distribution, right? Likewise, F has some kind of a distribution. It has some kind of a distribution. There is a distribution that is associated with F that is defined like this. That is defined like this. Ratio of two variances. Okay, and the distribution depends upon the degrees of freedom for the numerator and the degrees of freedom for the denominator. Okay, let it be. Let it be. So it has a distribution. And what is the hypothesis? The hypothesis is the numerator and the denominator are equal. The numerator and the denominator are equal. That is, the regression error and the residual error are equal. Okay, so essentially a bad model. It only covers halfway through. Regression error covers only halfway through. That's what it tells us. That's the hypothesis. So F, therefore, F statistic will have a value 1. That is the hypothesis. So centered around 1, we have this distribution, which looks like a normal distribution for large degrees of freedom. Okay. For very small degrees of freedom, it is skewed normal distribution. It looks like a skewed normal distribution. Okay. So for large degrees of freedom like this, it looks like a normal distribution. Okay. Since we are taking the ratio with always the bigger number at the top, okay, we always do one-sided statistics. One-sided hypothesis testing. Remember, the alternate hypothesis we always have is not equal to. Correct? In this case, we will have F is equal to 1 is the null hypothesis. F greater than 1 is the alternate hypothesis. Okay. So with that, we calculate to get this value to get this value for these degrees of freedom, what is the probability? This value or more. 1 is here, 98.17 is here. From 98.17 and above, what is the probability? When we ask that, we get this number. Okay, so let me make this number meaningful such that we can see what it actually is. Oh my God, you go any number, it's not, it's essentially zero. Let's make it scientific. It's practically zero. Oh my God.
Doctor, maybe you're looking at the format only. Actually, the value has been revealed at the other side.
Say it again.
Please format the cell and you can see the value. Actually, it's not zero. It is well formatted.
The format
See upper.
here.
Not the format code. Format code is always zero.
Where is format code is always zero. So
actually you have did the formatting well.
So what should be the format code here? I do not know. Okay, so looks like this is practically zero. Okay, if you want, we can do something like is equal to f dist f dot dist of the value numbered, comma degrees of freedom of 1, comma degrees of freedom of 2, comma true TRUE. Okay, so let us say